Hi, and welcome to lesson 17.1, which is all about representing linear non-proportional relationships. And we can use tables, graphs, and equations to represent linear non-proportional relationships. So uh, we can use an equation to describe the relationship between two quantities in a real-world situation, such as this, going bowling. So this equation here gives us the total charge for one person, Y. Renting a pair of shoes and bowling X games at Baxter Bowling Lanes based on this information here, $3 per game. There's a $3 per game, and the $2 for the shoe rental right there. So what we're going to do to make a table is we're going to first figure out, well, what kind of X values, number of games, what makes sense. Well, how about 1, 2, 3, 4 games? At most 4 games. And you can't have 1.5 because you're not going to pull a half game. Usually not. And so using our equation here, we'll plug numbers in for x. So we have one game, so 3 times 1 is 3 plus 2 is 5. And that's what they did here. 3 times x, 3 times 1, because x is our number of games here, plus 2 is $5. So you're going to spend $5. And 2 games, 3 times 2 is 6, plus 2 is 8. 3 times 3 is 9, plus 2 is 11, and 4 times 3 is 12, plus 2 is 14. So there's our table of values. Okay, so your job is to figure this out for Francisco. And he makes $12 per hour doing part-time work on Saturdays. He spends $4 on transportation to and from work, and this equation gives us his earnings after transportation costs, working for X hours. And here's the $12 per hour, and you have to subtract 4 because he spends $4 on transportation. So uh, we have a table, and on that table I decided to say the scenario is, what if he works 2, 3, 4, 5 hours, or 5 hours? And for 2 hours I would do this. 12 times 2 is 24, minus 20 minus 4 is 20. And 12 times 3 minus 4, well, that's 36, minus 4 is 32. So he'd make $32 if he worked for 3 hours. And that's what the rest of my table is here. For 4 hours is $44. For 5 hours, it's 12 times 5, which is 60, minus 4 is $56 he would make. Okay. Next, examining linear relationships. So let's remember what we know about proportional relationships. And it's where we have two quantities, which the ratio of one quantity to the other is constant. And that graph is a straight line that goes through the origin. And I remember the y equals kx. That's our equation for a proportional relationship. K is the slope, the change in y over the change in x, just to remind you. So we have this here, and the entrance fee for this theme park is $20, and visitors can they can purchase additional $2 tickets for rides, games, and food. And this equation here gives us the cost to visit the park, including purchasing some tickets. So it's $2 per ticket, $20 to get in. That's where those numbers come from. And if we were given these values for the number of tickets, 0, 2, 4, 6, or 8, and I plugged them in here, 2, 4, 6, 8. 0 is easy because that's just 2 times 0, which is 0 plus 20. That's $20 that you're going to spend just not riding any rides. You buy 2 tickets, that's $24, as I did here. 4 tickets, $28. What, 8 plus 20 is 28. 2 times 6 tickets is $12 plus 20 is 32. And if you buy 8 tickets, that's $16 plus 20 is $36. Here's the table. Okay, let's plot this stuff here. And I got a lot of stuff going on here. So when I plot 0, 20, 0, 20 is here. 2 and 24 right there. 4 and 28, 6 and 32, and 8 and 36. I know I have a lot of other dots, but I'll explain those other dots in a moment. So let's describe the shape of the graph. It's a straight line. It's on a line. And find the rate of change between each point. And what I could do here is I could take the change in y. So the rate of change is the slope. So it's change in y, 24 minus 20, 24 minus 20 over 2 minus 0, 2 minus 0. And that's 4 over 2. And 4 divided by 2 is 2. $2 per ticket. Is the rate constant? Yeah, the rate is constant. I mean, I could do this all day. What change in y, change in x, what subtract these, that's 4 over 2 and the whole thing. But this visually says, oh, that's a constant rate of change. It makes a straight line. So, if we calculate rates of change for the values in the table, explain why the relationship between the number of tickets and the total cost is not proportional. Well, if I do this, if I take the proportional relationship means I take y divided by x in every column and I get the same number. Well, 20 divided by 0, that's undefined. 20 divided by 0, right there, undefined. 24 divided by 2, that's 12. Right there, it's over. It's not a constant rate of change. It would have to be 12 and 12 and 12 all the way through. So the ratio of the total cost and the total number of tickets sold is not constant. I know I have these other things, but I got 28 divided by 4 is 7. Yeah, 28 divided by 4 right there is 7. 32 divided by 6 is about 5.3, and 36 divided by 8 is 4.5. But again, you could just stop right here and see, oh, not a constant rate of change. Now, would it be possible to add more points to the graph from x equals 0 to x equals 10? So this is the x-axis. So they're talking about, could you have 1 in here? And let me zoom in here and show you that, yeah, you could. Not only do you have the even numbered amount of tickets, but you also can have odds. So that's 1. 1 is here. You can buy 1 ticket. You can buy 3 tickets, and so on. If you bought 1 ticket, that would be 2 times. That would be 2 times 1, which is 2, plus 2 plus 20 is $22. That'd be $22, and that looks like it about fits there. So you can buy other ones. So yeah, you can have. Oops, let me zoom out. I'm getting a little lost here. So if you bought 1 ticket, like I said, it's $22, and here are the prices for 3 tickets, 5 tickets, 7 tickets, 9 tickets, 10 tickets. But here's the other question: would it make sense to connect the points with a line? No, I would not connect this with a straight line right there, because a straight line would mean that you would have data in between these points here. Like you would have a half ticket, or you would have 1.5 tickets, or 2.3 tickets. No, you're only going to have the number of tickets here. So here, the number of tickets can only be a whole number. So that is that. Now, what we got is more representing linear relationships using graphs. So a linear equation is an equation whose solutions are ordered pairs that form a line when graphed on the coordinate plane. And that's what this was here. This was a linear equation because when I graphed the ordered pairs, these are the ordered pairs, when I graphed them on this line, it made a straight line. That's what a linear equation is. That's what this statement is saying here. Linear equations can be written in the form of y equals mx plus b. That's super important right there, where b is not equal to 0. And the relationship between x and y is non-proportional. So this is not going to go through the origin. In this situation, the diameter of a Douglas fir tree is currently 12 inches. So the diameter is from one end all the way to the other, going through the middle. Is measured at chest height. Okay, over the next 50 years, the diameter is expected to increase by an average growth rate of 2/5 inch per year. And this equation gives y, the diameter of the tree, in inches after x years. So we're asked to draw the graph of the equation, describe the relationship. Okay, if I put 0 in for x, this is going to be easy because 2/5 times 0 is 0, and 0 plus 10 is 10. So they decided to do this in multiples of 10 to make the math a little bit easier. So 10, you have to think this with me here. 2/5 times 10. Well, 2/5 times 10, that'd be 20 over 5, which is 4, and 4 plus 10 is 14. If you put 20 in for x, you would get 18 for y. If you put 30 in for x, get 22 for y. And if you put 50 in for x, you'd get 30 for y. So when we plot these ordered pairs, 0, 10, right here, 10, 14, here, 20, 18, 20, 18, 30, and 22, 30, and 22, and 15, 30, we get a straight line. Draw a line connecting the points to represent all the possible solutions. So in this case, we would connect the dots because time is we'll have a value of time. You could have 10 years, so you can take half of that. 5 years, you have a value at 1 year and 1 month, and you can have a value at 1 day. You can have a value at 79 days or whatever. So yeah, it does make sense to connect this because you can have a value for every moment in time. Okay, so what we have is this, and I'm going to cover this up. So we have this. I want you to make a table and a graph and graph the solutions of the equation. So there are x values, so find the y values and graph it. Okay, so what we got is this 529. So x is -1, 0, 1, 2. And I have that equation, -1, 0, 1, 2. And we have -2 times x. This is from our equation. So when I put -1 in here, I do the math, and I get 3. When I plug in 0, I get 1. When I plug in 1, I get -1. And when I plug in 2, I get -3. So these four values, 3, 1, -1, and -3, I place them here in my table. Say 3, 1, -1, and -3. And then these are coordinates, -1, 3. -1, 3, -1, 3 is here. 0, 1, 0, 1 is right there. And 1, -1, 1, -1 is there. And 2, -3, 2, -3 is there. And it makes a straight line, linear. Isn't that fantastic? And that's what you got to know about the linear equations, the linear relationships when they're proportional and they're not proportional, and yeah, and using them in a real world situation. That's it. Thanks for watching.